Very complex level we don't understand. Okay, so let me explain something to you people. Can someone open whiteboard? I want to see how well you people can understand a question. Here is where I'm going to pose a question, not going to give you an answer.
Maria?
Yeah. This has some relevance to the recent moon mission of India, or in general, any mission that leaves Mother Earth.
Yeah.
Maya, how much time did it take you to get used to the tablet?
Actually, it's only when I started using it for this that I got used to it.
So pretty quickly, is it? I'm planning to order one tonight. It's always weird for me to just wait around for someone to join in with graphics tablet and write. So I'm fed up of
Right, it's worth buying because it's quite useful. By the way, I have one in my office. Maybe Atharva, you remind him, I can give you one.
Okay, sir.
You can use and return it back when you graduate. Or if you can promise me 5 crores for Coders I 10.0, you can keep
So
it.
funding is better.
Okay, done, sir.
Better deal.
Okay, so see, write down 3 people. Let's say Chetan, Anurag, and Bharat. Wow, we have ABC there. Cannot think of a better example. Anurag, Bharat, and Chetan. A, B, C is a vector. Okay, write down some values of the money they make today in their business. They compete with each other basically. Okay, so write down. Let's say A is 10, B is 12, C is 9. Next day, it is 15, 7, and 10. And next day, it is 9, 9, 10, 10. Next day, it is 10, 10, 8. Okay, you see what's happening? The sum is more or less the same, right? All of you, please concentrate. Here's a very real world example. क्या चल रहा है यहाँ पे ABC? What is this? In thousands returns of Chetan, Anurag, and Bharat. Is it clear?
Yes, sir.
The sum total should be more or less the same always because you have same number of people coming and eating in the restaurants. ABC are 3 different restaurants in the same campus, let's say. Population is not very floating. Of course, on a fest day, there will be a lot of people. Let's remove that. That's an exception. Okay? Done?
Yeah.
Without loss of generality, we'll even assume that the population is constant here in this campus. But still, returns में थोड़ा अलग-अलग हो रहा है ना. 10, 12, 9 is what? Can you write the sum at the end? Yeah. Total? 31, 32, 29, 28. You see, it's around 30, right?
Yes,
Let me give a pause here and then let you people think. Is the problem clear, guys?
No, sir.
Okay, go ahead, discuss for a minute.
So we have like the sum of like everybody is contributing something, and they're approximately contributing the total of everyone is approximately the same in each case, right?
Yes, why is that true?
uh, because we have our data is in that form, maybe.
Yeah, like we can actually think of a lot of real life examples, like in restaurants when the amount of quantity of food would be the same, right? So once the food runs out, you can't serve people. So the total amount of food would be same across, like assuming they make the same quantity of food each day, then the amount of food sold might obvious like kind of be constant, right?
Okay, right. Good. Go ahead.
Yeah, so yeah, some other example I thought of was that assuming Anurag, Bharat, and Chetan are living in a hostel, and in the morning, approximately 30, maybe let's assume it's the amount of milk or something they consume in a month. So you buy approximately 30 liters in a month. So and that's fixed, and then the amount of consumption of each of these people would be different, but the total would approximately be 30.
Can you just give us a brief of what we have done till this point? There are new people as
Okay. So we just took an example of some data where across the rows, like this sum of contribution of each row is approximately equal. It's around the same range. Like we can notice that in the first row, 10 plus 12 plus 9 is 31. 15 plus 7 plus 10 is 32. 9 plus, oh, are there more people entering?
yeah.
Okay.
You can continue. You can continue.
Yeah, so across a row, in 9 plus 10 plus 10 is 29. 10 plus 10 plus 8 is 28. So we notice that the nature of the data that we've taken here is something like uh, the total amount is approximately constant. It's not exactly the same, but yeah, it's approximately same. So what can we observe from this? That's the
Oh, so maybe we can think of it like one of the column is dependent on the other two columns, because some of some of all three is same, right? So we can write the third one as the sum minus the first two columns.
Possible. I have another way of saying it. Very good. Now we are talking. The way you see, Anurag has made 10,000 today. Bharat has made 12,000 today. Chetan has made 9,000 today. From their income, they do something and then get the money for the next day. This may not even be restaurant. It could be some other business on the busy suburbs of Delhi. Okay, or it could be any complex thing. Right. So let's not worry so much about the example here. But you observe that the previous day's income might have an impact on your next day's income. Bharat has earned 12 today. And so he invests more the next day, but he ends up undergoing loss. Because Usdin, maybe Idli sold a lot. And he thought of investing more on Idlis the next day also. But South Indians were less in number there. Right? And he underwent loss. While many of them who came went to Anurag's restaurant. Right? The next day it was evenly distributed for some reason, etc. etc. Kuch to ho raha hai yahan. Maybe the previous day's data, if fed, gives you the next day's data by using a matrix. Then we say this has a linear relationship. इस पे थोड़ा आपको दिमाग लगा के सोचना पड़ेगा. डिस्कस करना पड़ेगा कहां से मैट्रिक्स लेके आ गया वैसे ही हाँ? Well, I mean, am I forcing in a matrix here, or is it naturally occurring? What does the matrix even mean here? Go ahead. We are talking about a very popular concept that is close to 65 years old, which has taken the field of electrical sciences, physics, astronomy, computer science to the next level.
So
Think what
in
am I
that,
saying? Yeah.
in that cancer antigen sheet, we were finding relation between the columns of the data, right? So in this case, maybe we can find a relation between the rows by the similar method.
Can you predict what will be the 5th day here of Anurag, Bharat, and Chetan's income? Maybe it's possible, it's not possible. Right? We don't know. Now, let me write something here. I hope I can write on top of this. Let's see.
So, yeah, there's an option called annotate. So it
Annotate, exactly. I'm just trying to see that. Where is it on my iPad? I don't know. 1 second.
Average, give us the
Sir, it's on the
base
side
salary.
of AI companion. Like there's an option called annotate.
And that depends on the OS and the device also.
Oh, yeah, yeah.
1 second. Looks like I don't have. I'll quickly use the whiteboard then. Oh, am I the host?
You're the co-host. Should I
Co-host. No, don't worry. Okay, let me start writing here. Okay, you see what I'm doing now? Anurag, Bharat, and Chetan. Today's vectors and the next day's vectors. I'm sorry for my handwriting. Not in the very ergonomic situation right now. And so on. This is a vector, this is a vector. Okay. And so on.
So here the days are represented as column
Right.
vector.
Yeah, column vector, correct. This is the first day. This is day 1. This is day 2, and so on. My question is, maybe there's a matrix M, which when applied on day 1, which is a vector, gives you day 2. Can Maria copy this onto her notes?
Okay.
And in reality, what happens is what you get in day 1 has some complex relationship with what you get in day 2, has some complex relationship with what was in day 1. Okay, this is in reality. Okay, but when you observe it, you end up actually getting delta 2, which is because there is some noise.
So in real life, if we think about finance, world of finance, stock prices, right? Every day, if you go to NASDAQ or NSE or Nifty, most of us know Sensex, which is 30 stocks, Nifty 50 stocks, the top companies. So typically, if we monitor stock price of a particular company, I know today's price was 230 rupees. The next day would be somewhere in the vicinity. So we know that if I'm interested in predicting the stock price of tomorrow, Either it can go up or down, but if it is going up, of course, I want to buy today. But if it is going to go down, maybe, I'll have a different strategy, right? So these are used by traders. It's a very, it's actually $1 billion problem. Every day, if you look at it, thousands of crores gets, and if we we are in a prediction business, if you even 55% right, we'll make a lot of money. So it is actually a very, very prevalent and used in real life, particularly in finance.
Correct. But then, if you remember, we have discussed what is called statistical arbitration, where once you see that, I'll tell you one small experiment which we did. Atharva, can you tell us the Sensex program that you wrote?
Yes, sir. I'll open it.
Okay, maybe you can copy this onto your slate, Maria, and you can.
Sir, actually, the whiteboard is view only. Like I only have permission to view, so I think
you can edit now. Also, you can maybe make a manual note of this so that it's only 4 lines. I don't need anything beyond this. So getting back, Devasmith, Atharva will tell. The idea is here basically. Atharva, can you explain your code, Sensex code to everyone?
Yeah. So the problem statement was that we have data. We have like opening data and closing data at what price it has opened and what price it has closed for like, I think it was 20-30 years maybe. And we had to find an algorithm such that we should find an algorithm to calculate the maximum amount of profit that we can find out, that we can gain from this.
Okay.
So that means you have to have a strategy: buy and sell, buy low and sell high. So
that's all.
Number of
sell high.
layers you can do, right?
Correct. Can you guess now? Here's a question, Devasmith. Actually, this is very counterintuitive. Can you guess how much money you would have made by now had you sold high, bought less from 1980 or 83, whenever Sensex was started? What year was it, Atharva? From which year are you looking at the data?
I'll check.
Yeah, roughly some 1980, let's say 40 years, 43 years. How much money you think you would have made now?
Okay,
rough guess.
So roughly there are 200 trading days because in a year, 200 or 250 trading days. We're talking about 40 years, so that's basically 10,000.
You start with let's say 100 rupees.
100 rupees. If it is 40 years, typically I know stock market gives around compound annual return of 12 to 15%. So every
I'll tell you the bias that you are making here. You are assuming that you are getting the average returns.
Correct.
But what I'm saying is buying high, selling whatever, selling.
So it is
high,
more actually. Yeah, it's actually going to be more because nobody gets it right. You have to get it right every time, right? That's
every time. Exactly.
Right.
Exactly.
So you are probably the luckiest trader on the planet Earth, right?
Exactly. How much money will you make? Rough guess. You got it right.
This would be, I think, almost. I guess every year you'll probably double. So 40 years means 2 to the power 20. So if you spend a rupee, let's say
a million,
something like that.
Okay, Atharva will tell us the answer now.
It was like 10 raised to 24 rupees, I think.
So 2 to the power 20, not
2 to the power 70, 2 to the power 70 or 80. Yeah.
Wow. No, sir, it was 24, I think.
No, 2 to the 10 to the power of 24.
Yeah.
It's 2 to the power of 70.
2 to the power of 70.
Okay, so I missed it by a huge margin.
Yes, 2 to the power of 70 is 1000 to the power of 7 roughly.
So
Okay.
if you made that amount of money, basically you have considered entire world's wealth in your pocket.
No. Wait. It's a lot more than that.
Correct.
It's a lot more. It is 1000 to the power of 7. Can someone tell us how big that is?
1.180 into 10 raised to power 21.
No,
So I think
how much billion, trillion is it? How many zillions is it?
So just to put a perspective, today, as per RBI report, the entire saving, entire fixed deposit in entire India, across all banks, all Indians, is 90 lakh crore, 90 trillion.
90
So
trillion, right?
90
So
trillion is
what
the fixed deposit.
okay, what we are now saying is 1 million trillion. No, 1 million zillion.
Yeah, we even
7.
don't have that amount of money in our
Yeah,
system.
I mean, it's like the next 10,000 years, if we were to work, we cannot make so much money. One person will make if he has timed it properly. So timing share market is a huge conundrum, simply because if someone were to be timing it, then share market will close down. That's all.
Yeah.
BSE, NSE will go away, right? Because
So
he will
I
be making
think
all the money of the world, not necessarily the country, but the entire world will be under him.
Even Las Vegas Casino, who actually look at the randomness, right? Since we are talking about that, they have statisticians who actually monitor the randomness of each device because they want to make sure that expectation of those errors are actually zero. Otherwise, if they see a certain bias, then the house will lose money. So they actually go and shut down that machine and try to fix it. Yeah. Similarly, now stock exchange is happening at a data level when there's a lot of players buying and selling.
That is arbitration, where if one person is earning, he will induce disinterest in others automatically. Either others will quit, or his idea will be hacked and others will start using that idea, or someone will better his idea and stuff like that. So anyway, so the law is that within a few days or weeks, you make a lot of money if you have a hack, right? But after that, the hack should not work, philosophically and scientifically speaking, right? Anyway, so getting back, you have this, maybe Maria, have you shared the screen?
Yeah, sure, sir. Like, I've just taken a copy of the image actually. Yeah, I'll try.
Okay. So the idea here is there is a, I'm trying to, the last line, if you can see, I'm considering the next day's prediction based on today's prediction. Because even today, I do not know. It's yet to come. I'm making prediction after 100 days. The problem is noise gets added up so much that if I discount it, I will not be getting the accurate values. So the idea is to estimate the noise here. Thoda complicated hai. I just gave you a glimpse of what's coming next. Once you people finish LinAlg 75, I'll discuss this in detail. Okay. Simple carbon filter used in many aspects of science and engineering, especially missile launching. All your iron domes, make use of carbon filter or advanced versions, variations of carbon filter to detect if the missile is actually coming due to error in this direction, or it is launched in that direction. Though alag hai na? Missile is coming this way. You should detect that is this direction at the very accurate level, at the centimeter curvature level. Is it going in the right direction, or is it direction plus noise? Then if you remove the noise, you will get to know the intended destination of the missile. As of now, generally you throw a ball, the ball is meant to go and hit the wicket, but it doesn't hit the wicket. Right? Missiles also do that.
So this was used in real life. Actually, if you go back to 90s, when there was a Gulf War between Iraq and Iran and then US. So Iraq used to fire Scud missiles. And for every Scud missile, because of this error you're talking about, there used to be 2 Patriot missiles that used to go to remove that error. And so that way that missile gets nullified. So this is actually a real life example of, how this error, if it is not within the appropriate confidence interval,
Threshold,
then you fire another one So that way you cover the probability of nullifying the Scud missiles.
And you see, there are twofold problem here. One is when you launch the missile, you should understand the error with which it will propagate. Second is when an Iron Dome is detecting it, it will detect with error in mind only. I'm seeing a ball coming towards the wicket using my camera, and I want to detect whether it will hit the wicket or not. I'm not considering the direction of the breeze. That will result in a huge error, right? All these things are hidden in. I'm basically giving you. I'll tell you the article which I'm going to cover here. You guys can Google for it. 1 minute. 1 second. 1 second. 1 second. Google for this. Just a minute. Just a minute. Where did that go? 8 minutes. Kalman filter for the common man. Kalman filter for the common man. 1 second. 1 second. There's a reason why I'm asking people to see it. 1 second. Just a minute. Okay. Poor man's explanation of Kalman filtering, or how I stopped worrying and learned to love matrix inversion. Okay, let me just post it on the group. One of you can.
Yes, sir.
Yeah, you can post this. Maria, Chetan, Atharva, one of you.
Yes, sir.
Bharat, what time did you leave yesterday?
1 o'clock, sir. 1 o'clock. We have a upper limit of 1 o'clock, 1 a.m.
Oh, wonderful. So, Devasmith, you're not on WhatsApp, so I'm unable to include you. But we have a group called Starlight Scholars. Starlight Scholars. Entry there is only for people who leave last.
Okay.
What is that idiom? Good guys finish first. What is it?
Good guys finished last.
Last is it? That should be the idiom for the Coders Eye group, but it's the original idiom is something. Good students finish for something like that. Anyway, I forget it. So it is Kalman filtering, Kalman, but your autocorrect always corrects it to Carman or Carman or Karma sometimes.
Yeah. Kalman. Okay, it's the person's name.
Kal.
Oh.
Kal. It's the name of the person who came out with it and even got a very special mention and prize from
Is
Obama.
this the correct spelling? Kalman.
Perfect. That's right. That's right.
Okay.
Okay. So all the build up aside, it is basically the next state depends on the current state and a matrix application on it, plus some noise, right? You have to figure out what the noise is. All right, let this sink in slowly into your minds. It's easy to write the derivation and tell you what it's all about in half an hour's time, but then you will not be inspired by it. Let's go slowly. Let's do it the image way, the way we did yesterday. I'm very impressed with the way you people cracked the problem slowly. I think you understood the in and out of what we did yesterday, no? 1 pixel missing, how to get that. And the next level is, if many pixels are missing, you understand the idea of entropy there. All right. Anyways, so let's now switch to Kalman filtering for the next few days. Anyway, I expect you all to finish off with the basics of linear algebra, and slowly we'll take this up. And look at the beautiful title there. We didn't even share it here. Yes. Poor man's explanation of Kalman filtering, or how I stopped worrying and learned to love matrix inversion. So it shows how beautifully matrix inversion can be used to detect error in measurements. I'll give you the intuition for it. There's so many ways in which we can inspire this idea. The idea is you are walking in a straight line, but you're not walking in a straight line. What is the direction in which you're going? It is not a straight line, right? When you walk, it is not actually a straight line. But knowing your trajectory so far, can I detect your next 2 meters direction? You got what I meant?
Possible.
Yes, sir.
Yeah.
Right?
I think this is what we did in PCA also, right?
See, all these things are beautifully connected. You can always connect them with each other. But then here's a, let me post this as a geometry problem for you people on my whiteboard. Just a minute, guys. Someone sharing something. Excuse me. Quickly, I'll show you. See, I am walking like this. Okay. Now I stop here. Now, can you tell me, if I were to walk for 2 more centimeters, where will I be?
Okay.
Now, one obvious way of doing this is to simply join. I don't know how to change colors here. Okay, got it. One obvious way is to simply draw a straight line from here to here. It's not my notability, so I am unable to draw a straight line. Maybe I will draw a straight from here. You see? You see? Excuse me, guys. I'm sorry. I'm sorry. Draw this and extend this to 2 centimeters. That's one way. Do you think that's a good way? All of you got the question right? Can I stop sharing? All of you got the question?
Yes.
That's all is the question. देखो पूरा जहां पे common sense apply करना है वहां पे ज्यादा mathematics नहीं apply करना है. ये में पूरा common sense का question है. What is wrong in the straight line fit that I did there?
So you are making the straight line only connecting 2 points, the starting and where you are, right? And we know that it is not going in a straight line. So it's kind of making a little bit of error in every step.
Absolutely. Observe a
Right.
ball going or a missile going to its destination. You simply put a straight line from the beginning to the point so far and extend that by 2 centimeters is the worst ever approximation that you can think of the missile's next direction.
Right.
Right? You should consider the trajectory. Usko trajectory bolta hai. Right? Straight line definitely is a good candidate if it is moving around that straight line, the non-curvy path. Right? Now, if it's moving in a very curvy path, it's going like this, then what will you say about the next 2 centimeters? It is not beautifully like this. It's like this, let's say. Okay, very interestingly, I think they're using Kalman filters in calibrating my camera also here on my iPad. This is some new feature where you move and it moves with you. If someone else sits next and it zooms in, zooms out and all that. So it should know my trajectory, right, where I'm moving and then center it around my nose or whatever. So getting back, you should understand the noise and then you counter that noise and understand the trajectory. यहाँ पे इस क्वेश्चन में नॉइज का वर्ड का मतलब क्या है इतना समझ लो. The next discussion, once you finish linear algebra 75 and then finish all the modules, we'll cover this as one of the very important stories and application of linear algebra. We'll in fact crack this problem. I'll in fact simulate and show you a missile being launched and then landing, and you can actually find out where it lands. All this will be function. See, I'm not going to show you a very nice looking missile. Drama thoda kam hoga wahan pe, in the sense that I'll give you a function f, a Python function which spits out the coordinates in a discrete way, time series way. You must predict where will that be after k time steps. That's all. As Devasmith rightly points out, this can also be used for predicting the stock values of a particular stock, knowing its behavior so far. and predicting its trajectory in the next few days to come.
Sir,
Okay,
is
what you people?
LBW the same thing? Like when you predict LBW cricket, is it the same thing?
Yeah, it's the same thing. So you hope that it will go and hit the wicket. I think they I don't know what they do there. Maybe are they really using this kind of complicated algorithm there? I don't know. This
So,
is
so I'll tell
really
you,
using computer vision, by the way.
so they were discussing in one of the recent match, this Hawkeye is actually only one company in the entire world who has developed this system. There's no alternative. And a lot of people don't understand. So basically after this pitching, it's looking at the trajectory and there is an element of error. So we are not talking about error, they call it umpire's call and all that, half of the ball.
Yeah, see the way the seam falls and hits the pad, you put your leg before the wicket and you're predicting how it will go and fall based on how it has come up so far, while the ball is also receding in the sense that it is gravity is also a matter of, it's not just the trajectory that you're looking at, the parabola ka exact formula leke aana hai. How they are doing it, if they are monopolizing it, then it's their way.
So there is an average bounce of the pitch, but if the pitch has uneven bounce, taking an average bounce from a distance and then taking a theta and doing that, then you're talking about if we do a measurement of error, the error itself is quite large. So
especially if the place where the ball has fallen and the place where it has hit the pad, if the distance is very small,
yeah,
it gives room to a lot of noise in your estimation.
Yeah.
Right? That's very interesting how they do it. Maybe what company is that? There's
Hawk's Eye.
Hawk's Eye, is it?
No, Hawk's Eye.
Hawk's Eye, okay. Hawk's
Hawkeye actually. HAWK Hawkeye, yeah.
WK, I see. Very nice. Interesting.
So
yeah,
that's
so
one of the
Magnus
DLS.
effect.
When there is a rain, how do they calculate what should be the par score, right? Things of interest to us, right? Because the New Zealand professor actually came up with those methods. Previously, that was the first one which started from that Auckland University. Then the DLS came in. So, but again, there is math involved there because if you look at the resources that the team has, if the wicket falls, then the target, becomes
that's a complicated formula always.
Yeah,
right?
but
How
it's
to
interesting.
re-declare the
Yeah.
win.
Yeah.
Yes. In fact, Andrew was telling that one of the inspirations to start data sciences BS is IPL matches. He thought he can teach a lot of that. He even does that in his Stat 2 courses. Right?
Yeah, there's a lot of IP.
Yeah, the idea is to predict that, right? Okay, so the day when you can predict cricket, you need not ask people to play, right? That's the fascinating part of prediction, right? If you can predict something, why do you have to check? If the accuracy is so high, why do you want to even conduct that event, right? Anyways, so on to you people, finish the 75 questions and all the modules, and I have at least 10 such applications. If not 10, at least I'll do some 5 applications before going ahead. I'm also thinking of doing these things independently without building the basics. I don't think basics are required beyond linear algebra. Calculus to aapko pata hi hai. I mean, at the level of optimization, we use calculus. Otherwise, the rest of the things we can explain without developing the subject. Only linear algebra requires development because something at the level of inverting a matrix, whatever comes here, you may not understand, you may not appreciate what that is, right? Something at the level of matrix decomposition, at the level of eigenvalues, we use it extensively. Otherwise, you don't understand the physics of it. The structure is in the physics. The soul is in the physics. So to understand that, linear algebra is important. Otherwise, after this, I think most of the algorithms will cover it like a question and an answer. Start with the Kalman filter. Okay? Sure, on to you people. Go ahead.
You have your
Question.
vectors.
Yeah, I think we reached till question number 20 or
So
something,
before
right?
we start with linear algebra, I just wanted a quick brief for what we've discussed till this point.
You are very much less audible, Chetan.
The thing is that if we maybe I also wanted to clarify, like, what are the conditions based on which we actually, is there some like, does the data have to follow a certain property so that we can use the
Can you
previous data to
can you
predict
share
the
your
future?
screen? Can you share your screen? I could not follow the discussion because earlier I was sending out the messages and announcement. So
Like
okay.
I when I was trying to get the screenshot, I also lost, like I wasn't,
Mhm.
yeah, maybe someone else can also help here. So
Yes, I
the first part you were there, right? Like the total was almost same.
I
So
wasn't there
yeah,
when the data was written.
okay. So in this case, the sum of each row is almost 30.
Right.
Yeah, it's almost 30. There's actually, yeah, so if you there was some data here which I lost. Yeah, I can't move the image. Damn it. Yeah, so yeah, what was here was something like, yeah, so if these are like, if this row is something like
Now you the missing part that you are trying to fetch is only consists of two column vectors,
Okay,
A1
yeah,
and
two
A2,
column vector.
A1
do
B1
one thing.
C1, A2 B2 C2, and so on.
Okay, do one thing. Let's continue with linear algebra. I'll look into the recording and I'll see what we discuss, and then we'll give a brief tomorrow, whatever was covered till
Yeah,
this point.
maybe I also will check
No,
that out.
let me inspire you with something that you people know already. You've seen Markov chains, right?
Yes.
Markov chain is, there are four or five different states. You look at the proportion of people in different states. Correct?
Mhm.
Correct. Can someone recollect that?
The hostel, cafeteria, and the mess problem. Yeah, we saw in
Correct.
the initial lectures. Yeah.
Okay.
Yeah, this was in the initial modules. Correct. So wahan pe, it is not always that the janta's sum is the same. Some people will fall sick and go back home. Some new people will come in. How will you estimate? That is the question. That's all. From one state
Answer
to the other,
this
use a transition matrix. The transition matrix assumes a happy world,
right.
right? The best case that nobody goes missing, nobody gets added. What if someone's getting added, someone's getting deleted, and that is coming from a distribution, if you know what I mean? Don't break your head much about if you don't understand what is a distribution. Assume a n01 there,
Yeah.
right? Or a
So,
n0 alpha there.
So I'll tell you the real life example of where it is used. All the banks use
I
it.
think David Smith is now inspired. You can give them some examples surrounding this.
Yeah. So it is actually again $1 million problem, because every bank every month lends hundreds of crores of loans. So these accounts basically can take be in a 2 or 3 states, right? Because it's basically hostel, mess, all that. These are all different states, and there is a probability attached to each state. So account or a customer can pay their bill on time, or there may be one cycle delinquent and next two cycles delinquent. Or if you don't pay for 3 months, then it's a bad loan and the bank loses money. So really there are 4 states. What the bank's data science team develops is the probability of each account or each customer staying in current bucket, or they call it bucket 1, 2, or charge off, right? So if keeps on happening, so what happens is there is a 2 way of estimating it. If you're taking about accounts that were booked 4 months ago, you assume it's a closed block, nobody drops off or nobody gets added to the pool, then it's kind of very similar to the example that Sarah discussed, right? But in reality, what happens? Every month, some customer will close their accounts and some new customer will also be added to the bank's portfolio. So then it becomes kind of an open system. So when you are a risk manager, you want to keep some money aside as to how many losses will be there. You estimate how much losses are going to come from your existing customer, and how much loss is going to come from the new customer that came in, and all that. So it's actually a very, very real life problem, and that each bank that you bank with actually has to grapple with this, and every month they have to, as per RBI regulation, they have to actually produce that report and do what you call as risk capital calculations, and it's part of Basel II and all that. So it's actually not. It is very much used in banks and financial institutions, because this all deals with probability, different state space probability, and transition matrices and all that. So this is very much used in the industry.
But you'll observe that while yeah, the motivation is it's heavily applied, The basic idea is very simple. You are trying to capture the phenomena using matrices, assuming that the matrix captures the phenomena. This is exactly like the yesterday's form of problem that we solved. You assume that it is solvable using simultaneous equation wala ek idea. For all you know, it may not. You're taking a real life image of your face and you're bringing in simultaneous equation because that's all we know. Even here, all we know is assuming the world to be linear. Aaj ka state, kal ka state is captured by linearity. But what I'm discounting is the noise. I add that noise, estimate that noise, and you will surprisingly see that it indeed is linearly approximable. Understanding what I'm saying? And this is the simplest way in which you can put the problem. There is nothing much. If you're not understanding my statement, probably it's because of the jargons, the word linear, the word noise. All I'm saying is I am moving like this. Okay, you know that I'm going in this direction, but this flickering you have to capture. This flickering is given by your normal distribution. There is some uniformity in my flickering, right? That's always normal, they say. Right? That's the idea of Kalman filter. It filters out this noise to the extent that is possible. And there we'll bring in an idea of linear algebra. It's a beautiful amalgamation of linear algebra with in real life situation. So I'll take leave now. Huh? Take care, guys. Bye.
So it's like if we kind of filter the real life, real time data, we kind of get linear algebra, the problem set which could be modeled with the help of linear algebra. The only hindrance which comes along while modeling our real life situation is the error. So if we can find out that error and kind of subtract it or eliminate it, I will predict the
I think
error.
that's not like always the case. Sometimes the reason we can model it as a machine learning problem is because there's some noise. Like we saw that. I mean, the noise is not always a hindrance. Like that's what I feel.
Yeah. So if we see about that example sir gave, right, that line. So there are two things. We have to first define the straight line, right? So in order to define the straight line, we need certain bunch of points. Now those points are kind of deviating from the line in some sense, right? So we estimate the error. Once we kind of find out the errors, remove the errors from each point, then we can actually fit a nice line. That's one way to think about it, right? So the idea is to, if you can estimate the noise, and noise is supposed to be there should be no pattern or bias. Like if I take an average of the noise, it should be 0. Then there is some kind of random distribution, like the Gaussian noise, we call it, right? So if my noise has if I monitor the noise across all steps, on an average, kind of, the noise is 0, but there is a variance with a normal distribution. So that means I'm taking a random sample of that normal distribution and adding that to each linear step, right? So, and what I've seen is actually that. So that is what I think. Once we kind of take the data, filter out the noise, then what we have is remaining is the pattern. Then we can fit a linear model to the data. Then it's a classic regression problem, right? So that's the whole idea.
And then we can do predicting and all.
It's due to the presence of noise that you can feel like this is more from something I learned in like one of the lectures. Like there's some derivation where they're like linear regression, like with the okay, I don't remember it exactly, is equivalent to your data having some Gaussian noise. There's some concept related to that. I don't remember it exactly.
So there is a huge assumption that goes, I think it must have been covered in stats too. When we're doing a straightforward linear regression, we assume errors are normally distributed with mean, mu, and variance, whatever, sigma square, right? And they are IID. That means independent and identically distributed, right?
Yeah, we do.
Independent is a very, very critical assumption. However, in case of this example, when there is a dependency, on the previous state. So the errors are actually not independent. So error in time t is correlated with the error in the previous time. So this is where I think, fundamental difference between this problem we are discussing today
and
the classic regression problem that we encounter in everyday life. So in some sense, if I want to express mathematically, y is a function of x1, x2, x3. Here, y is over a time. Yt is a function of yt minus 1. I mean, y plus yt minus 2 plus error.
Like the noise is not independent. Like the error factor is dependent on your previous observation. Isn't
Yeah,
that would you? Yeah.
correct.
So when we try to fit the line, and in that case, we assume it's independent. Okay, yeah. Like otherwise, you can go ahead, yeah.
Yeah, I had a similar question. So basically, as our time goes on, we get more and more data. So I think after a point it would be impossible for us to compute it. So how do we decide how much data we need to consider?
Oh,
Well,
yeah.
I mean, I don't want to jump the gun, but the point is, when you are, there are different techniques people do, right? You subtract this, let's say stock price, right? You subtract today's price minus the previous day's price, what you call as so in other words, we have a function when you're subtracting, we're basically taking first derivative, right? So we know from math that if a curve is nonlinear, if you take a derivative, it degree reduces, right? And if it is nonlinear, if you take sufficient number of derivatives, then ultimately it will become linear. Right?
Yeah.
That's the concept, right? So same thing is applicable here when there is a dependency over time, and if you keep subtracting first level, second level, then once it reaches smooth, what we call as white noise, then you stop, right? So essentially, those are all methods that people do to. So there are techniques to monitor what is the correlation, lag, or not. We don't want to jump the gun, but there are methods to know what you need to do to quote unquote stabilize the error that's called autocorrelation and all that. So you may, if you're interested, you can look up, like there's something called a Dickey-Fuller test. All those hypothesis testings are there to know that your assumptions are valid, right? So that's. But anyway, today's discussion should be focused more on Kalman filters and what it does and how it helps us to make the prediction.
Yeah.
Next step, yeah.
Actually, yeah. So let me just. Should we go to the 75 questions now? Or
so what was
you
delta 1, delta 2 there, delta 2, delta 3 there?
delta 2 is the previous days, like the previous observation.
Okay.
So it's so it's some function of the previous observation.
Okay.
In case we have not understood it properly, there are people new as well in the session. It will not be
Yeah,
appropriate.
yeah. We can discuss this later, I guess, after more clarity.
Yeah.
I guess maybe if that's all right with everyone.
Pardon?
No, if it's all right with everyone, I think we can
I mean,
close this.
I would very much appreciate if somebody has understood everything that we have discussed this point to brief. I would very much appreciate that, but I don't see anyone who has understood everything till this point, and so I don't see any point right now discussing this.
Yeah,
If Davis Smith sir can help us out, then yeah, we can discuss this. Otherwise, we can continue with linear algebra 75, I guess.
I think We can do either one, doesn't matter. I think we kind of understand the problem, what Sir described. Do you believe that there is a gap in understanding?
So, Maria, you're sharing your screen.
I don't know the exact question till which we discussed the scientific question. So
23.
23. Okay.
Yeah. Can you stop sharing your screen for once, and maybe you can ask Vinay for the notes for XOPP file. Vectors.
You are, I guess, not audible, Maria.
Oh, sorry. Yeah, I don't think Srivane is there today.
Let me ask him.
Yeah.
You can till then we can continue with the usual notes, I guess. I don't think we'll get an immediate reply. Maria, are you there?
Yeah, sure. I'll just start it in a new document. Yeah.
I have observed a very, recent spike in this stock market and trading thing going on in our degree. A lot of
What do you mean degree?
I mean, in our program, in IT Madras, lately I've been receiving mails that they are having seminars and
Right.
launching.
We had
They also launched
one colleague.
a group, they also launched a society for this stuff, dedicated to this solely this stuff.
Okay.
Today there is actually a session at 6:37.
Correct.
Today itself.
Yeah. There was a guest gave a talk. In
Our
fact, last
tech
week,
love, I think.
last week also we had I think one of the professors, I forgot her name.
Of IT Madras.
Yeah, she also gave a nice lecture. I actually got that as well. Yeah, it's good stuff.
You won't find it here.
So
The
Darasit, sir,
PDF is there, right? Still.
The PDF is there,
can
but
you
not the
kind of
XOPP file.
can you kind of guide us, if somebody wants to dive into that stock market stuff via the data science channel through the tools of data science, what should be the approach of that newcomer?
I think understand stock market. I think I would kind of generalize it. Stock market is just a subset of what happens in the world of finance, right? So, stock market is what is called as market risk. So, the broad umbrella is called risk management. So there's a credit risk, operational risk. A lot of money is involved in lending. So a lot of energy goes into when you are lending somebody, is the person going to pay you back or not, right? So those are not related to stock market. In fact, even in India today, only 3 to 4% of the people invest in stock market, right? But if you talk about lending, it impacts 30 to 40% of the people have taken some loan from bank, right? So that's a bigger problem. So the entire industry is has many segments and subsegments. So when you're approaching it from a data science, we should think from an industry perspective, and then stock market is just a small portion of that. So depending on your interest, you can always specialize. But I would always suggest try to be more generic and apply generic knowledge, unless you are very sure 100% that you want to get into that space.
So are these societies which have recently come up in the sessions which are taking place, are they rightly oriented, sir?
Yeah, I definitely for last one, because I had a meeting, official meeting, I could not join today's, but then I go and watch in YouTube later on with a fast forward like 1.5x speed. Yeah, just to know what is going on. Yeah.
Let's start from the 24th question.
Yeah.
So the 23rd question was, when can two vectors in R-cube fail to manufacture a given third vector? Maybe since we have a lot of participants.
Can anyone tell us this? When can two vectors in R3 fail to manufacture a third vector?
A few people who are quite new. Maybe Himanshu.
Yeah, Himanshu. Even Ravi, I think Ravi is not. Ravi,
Yeah,
were
if
you
you
there?
want to try out that, if you can unmute yourself, or you can. Chetan, can you check the chat? Yeah, so.
There's nothing in the chat.
Yeah, there isn't, like, in case something comes up.
Yeah.
Yeah, so if you can unmute yourself, or you can drop it in the chat.
Anyone? We have discussed this if both vectors are parallel. Do we have parallel
Yeah.
vectors?
May I?
Yeah, go ahead, Swapnil.
Yeah, we discussed that the two vectors only form manufacture a third vector only when if that third vector lies in the linear combination of those two vectors, and if it is outside from that linear combination that it is manufacturing, then it won't generate that.
Correct.
Can you state this geometrically?
Yeah,
Swapnil?
I'm doing that.
Because Swapnil kind of mixes the geometrical statement and mathematical statement. That's why I asked.
Yeah. So let me take an example for this. So can anyone tell me a vector in R3? Any vector of your choice.
1, 2, 3.
Any other vector, maybe
7, 8, 9. Not audible, Maria.
Yeah, we've taken that example a lot of times. 1, 2, 3, 4, 5, 6, and 7, 8, 9.
no worries, we'll make
Yeah.
do with it. I guess we don't have any choice with that. So yeah, I have two of these vectors, right? Tell me any other vector as well. Third vector, not something that we have used before, not something that we generally use, something different,
0 to 4.
acceptable. So I want to see if I can manufacture this vector 0 to 4 with only the. Okay, I guess. Okay. Okay, let's see. Let me change the color for this as well. Let me make it red so it stands out. I want to manufacture this red vector with the linear combination of this green and blue vector. So what I'll do is I'll take A times U plus B times.
Then can I rephrase the question for? I'll take just 15 seconds. Okay. So the question is, as we require 2 points to draw a line, I guess we have now that awareness that we require 2 vectors to draw a plane. Fine. So the question is that we have two vectors, and it is very obvious then that they are going to form a plane. The question
Okay,
is,
okay,
we
let's
have a third
stop there.
vector.
Let's stop right there, Nishan. I just got a point that I wanted to just clarify before we move on that. So the question never said that we have to deal with a plane, right? The question never said that. The question only mentioned that given two vectors, can you manufacture the third vector, right? Say I am taking another vector. This is my third vector. Yeah. Can you take a look at this, guys? This is my third vector. I want to see whether I can get the vector 0 to 4 with some linear combination of these two vectors, u and a. Can anyone tell me that can I get that by taking the linear combination of the green vector and the purple vector? Can I get the red vector?
No, you won't be, because since they both are lying on the same direction, uh, or we can say that both are like a scalar multiple of each other, so we cannot change its direction by just multiplying
Mhm.
with some magnitude.
Okay, let's see. Let's see. So let me change this to say Z. No, I can't do that. Okay, let me take, say T vector. Okay. So let me do A times of U plus B times of T. Okay. What are we going to get here? I just want to observe that. I just want to observe that can I get this point? Oh, sorry, can I get this red vector by taking the linear combination of these two vectors? So this is the resultant vector. Let me make it some other color so that it's easily visible. Let me make it orange. So this is the vector that I want to see that can this vector reach this point. I'm just going to vary this vector and see what we are getting here. Can anyone tell me what are we getting here? Guys? If it's taking some time. Yeah. Yeah. Can anyone tell me what are we getting here? Anyone? Can I get this red vector by taking the linear combination of the red and green, so the purple and the green vector? Is it possible? What are you observing here?
We can also understand this by taking the parallelogram method. Like if we take the two vector that are lying
I don't
on
know
the same
parallelogram,
direction.
Swapnil. I don't know parallelogram. I'm asking you that can I reach this red vector by taking the linear combination of the purple and the green vector? What am I getting
Yeah,
by taking the linear combination of the green vector?
a line.
A line, right? And does this green red vector lie on that line?
No.
It doesn't, right? So I can, no matter what values I change for A and B, I can never reach this red vector, right?
Yes.
Okay, perfect. Perfect. Yeah, now Nishan, you can continue. I just wanted to clarify this point because it wasn't mentioned in the question that our two vectors are not lying in the same line. Yeah, good.
Yeah. So I was
You're not audible, Nishan. Is it just me? Perfect.
Am I audible now?
Yeah, no, perfect.
So I was saying that as we know that we require 2 points to draw a line. Fine. So we can say it vice versa that if we have a line, so we can say that 2 points constitute a line. That is to say, it is sufficient for us to have 2 points to draw a line. Or we can say 2 points constitute a line. I'm saying the same thing in different ways. So similarly, I guess now we have wisdom. What happens when we have two vectors? Two vectors constitute a plane, don't they?
The span of two vectors give you a plane.
Huh? That is what I'm trying to say. That as 2 points gives us a line, two vectors would give us a plane. Fine. And generalizing it, if we kind of take alpha times a vector and the beta times another vector, it will constitute a complete R2 plane or complete plane. But if we are going to kind of combine two vectors, it is going to give us a plane. By combining, I do not mean adding them. That's why I'm drawing a similarity between the 2 points are giving us a line and similarly 2 vectors are giving us a plane. So the question at our hand is that we know this is a very established fact. This is a very obvious fact that two vectors are going to give us a plane. And of course, two vectors are not lying on over one another. That is understood as well as Chetan just explained. So the question is, we have a third vector, random vector. So how do we know, or do we know, or don't we know, what could we say about that third vector? Is it going to lie on the same plane or somewhere else? In mathematical terms, what we say that the same way of saying this mathematically in the form of, in the language of linear algebra, is that we are going to take a linear combination of two vectors. By taking linear combination of two vectors, we talk about yet another technical term, what we call span. Chetan just kind of explained that how taking a different, scalar multiples of a vector give us it's a span, a complete straight line along that vector. Similarly, when we take linear combination of two vectors, that is to say that we take any scalar multiple of first vector and any scalar multiple of second vector and kind of add them, every time we are going to get a new vector. And if we kind of take the, what we say, what is that term, Chetan? If you can remind me, what we do, locus. What is the synonym of locus that we keep taking? So if we kind of, no, that's very much technical. That is the linear algebra term. Anyway, so we are kind of going to take a trace of every possible resultant vector, and eventually we get a plane. That is linear combination, and it's spanning a complete plane. So the question, this up to this point, I was kind of revising what we have already learned. That okay, we have two vectors, we are taking its linear combination, it's going to span a plane. This is very much jargonical. This is very much linear algebra centric explanation. I guess up to this point, we are very much comfortable. So the question at our hand is that we are given a third vector. And what could we say about that third vector? Does that lie on that plane or somewhere else? What could we say about that vector? That is the question. We are going to learn various possibilities that could arise out of that vector, I guess, with the help of course, GeoGebra and all. Yeah, yes, Chetan.
Okay. Okay. So I just want to clarify just a couple of things here. Just paraphrase them, not clarify. So these terms like span, linear combinations, we've discussed these multiple times. I'll again go and just repeat those once again. So just linear combination uh, only means you are taking the vector addition and scalar multiplication at the same time. You have vectors, and you're taking the you're taking the scalar multiplication and vector addition at the same time. You're doing all of that at the same time. That's called the linear combination. Uh, you see here, I have taken the linear combination of the vector u and the vector v. I have multiplied a scalar with vector u. I multiplied another scalar with vector v, and I've added them both. So that's the linear combination of those two vectors. And the span means just a very simple thing. All the points that you can reach or manufacture by taking the linear combination of any vectors. That's the span of those vectors. If you have one single vector, the maximum that you can span, can anyone tell me with one single vector, what is the maximum we can span, maximum points we can reach? Anyone?
All we need
And
to do is multiply it with various scalars, infinite scalars, make a trace of all those points where we can reach. That is the maximum span of it. That is the span of it. There is no kind of definition what is the span of a line of one vector or two vectors. Just put it to the test. Whenever we are given a task of making, whenever we are asked, okay, we want a span of something, take the scalar multiple of it, not a scalar multiple. In the given example where Chetan asks about span of a vector, all we can do is to multiply with a scalar and see all where it can reach. Make trace points, join them. That is the span. That is the way. That is the path where it can ever lie, and that is what Chetan means by span. उसकी पहुंच कहां तक है, संभावित पहुंच in हिंदी, probable reach, probable reach. No, on different days he or she can try different approach. Okay, I'll fire with 5 megapascal today, 10 megapascal tomorrow, and to reach a particular point. Fine. So on different days he is going to try it with a different strength and different effort. So we are going to tell him, okay, whatsoever effort you are going to put, this is your span. This is your range where you can reach. This is what Chetan is trying to explain. And of course, and we make all those points. Every day he's going to reach a point and we are going to mark it, okay, this is the point. Next day we are again going to mark dot, okay, this point. And eventually we are going to kind of connect them and tell, okay, this is where you are reaching and this is your limit. This is your kind of path where you can trade. This is your signature path. Yes, Chetan.
so, as Nishan very beautifully explained the linear combination, so linear combination and the span. So,
Span
s- span.
span of a line, that's all.
Hmm. So
Explain.
span is just the points you can reach or manufacture by taking the linear combination of one or more vectors. So that's just the span. And how do we figure out that if my third vector is lying on that? Can I reach my third vector by taking the linear combination of two vectors or not? I simply check if that third vector is lying on the span of the two vectors or not. If it's lying on the span of those two vectors, I can reach that vector. If it is not aligned, then I cannot. I cannot manufacture that vector by taking the linear combination of those two. So, uh, if you take a look at it here, I have plotted the span of the two vectors u and v. And can anyone tell me whether this red vector lies on that span or not? Anyone?
Yeah, from this angle, it looks like it is on that plane.
Yeah, it is, right? It is looking like it's on the plane. Let's see. Let's see. Let me plot the plane itself. Let's see if I uh so I have the two vectors, that's 1 comma 2 comma 3. Uh then I had 7 comma 8 comma 9. Can you look at the yeah? Can you all look at this? Can you all see this plane and the two vectors 1 comma 2 comma 3 and 7 comma 8 comma 9? That they are lying on this plane, but interestingly, the third vector we took also lies on this plane. That means I can reach that vector by taking the linear combination of the first two vectors 1, 2, 3, 7, 8, 9.
Hello, Chetan. Did
Yeah,
you change the vector that I have given, or it
you,
just that only?
yeah,
Because I
you,
just gave the random
yeah. I
this
did
one.
not change the vector. You told me 0 to 4. I inputted 0 to 4.
Yeah.
Like, do you
So
want
it's
to
just
try
a
out some different vector?
no, no, no.
Hmm.
I just gave the vector randomly and it lies on
Yeah,
that.
that's why when you gave me that vector, I was smiling because I knew that it's going to lie on the span of the two vectors. So I wanted some random vector that, but yeah. So we observe that we are having the vector that is lying on the span. So we can manufacture this vector by taking some linear combination of the existing vector. So let me just see that if what is the value that we can change to get that vector for E and B of obviously if we can do that. Okay, I think it's somewhere along this value, somewhere close to this value. Uh, yeah, can you see that just by varying those two knobs, I could reach this point, right, guys? Yeah. Okay. Okay. So this is what that question said. Maria, can you share your screen?
So we were talking about this was the 24th question, right? Till 23, I think it was explained. So we looked at an example of a linearly dependent set. We saw that these three vectors geometrically would lie on a, like if we are in R3, these three vectors geometrically would lie on a plane. So we saw that using GeoGebra. Is there anything more that needs to be discussed?
So we have, if U, V, W are such that a vector in this set can be manufactured by some vector in same set, then such a set is called a linearly dependent set. And we observe that visually as well, how that linearly a dependent set would look like. So any vector in on that plane would make a linearly dependent set, right?
So in this case, it was just a random guess happened to happen. This is just pure,
Right.
Yeah.
random chance. Yeah. Otherwise, most of the time you would have picked something else, which is
Right.
probably 1 out of 1,000 times. It will rely on the plane. So yeah, it's funny that you come up with a random example which lies on
Lies on the plane.
the span of these two vectors. Yeah.
Yeah.
If it's not linearly dependent, it's called linearly independent. Yeah.
Yeah.
Give an example of a linearly Oh yeah, that's the second next question actually. Yeah. Now cube and get conversant with yeah, we kind of saw that, right? Linearly dependent set in R cube and get conversant. Maybe I'll write down the example which you guys took. 1, 2, 3. Then there was 0, 2, 4. I don't remember the second vector. What was the second vector?
So we can always
Yeah, 7, 8, 9.
X, Y, Z, and it has to multiply
Yeah,
on
yeah, we can
side.
find that
So
out.
we can
Yeah, yeah.
actually find that yeah, when it dot product is 0 with both the left side and the right side. But then you have X, Y,
Dot
Z.
product.
I mean orthogonal, right? So then they're not going to
I didn't
may
get
not be actually
you.
not even orthogonal. You can be at an angle only two.
Yeah, yeah. So maybe we can find the factors in this case as well. We saw that in GeoGebra, right? Do you remember the exact values?
5 and minus 0.7, I think. That was the values.
5 and minus 0.7 or something like that. Minus 7.
Minus 0.7. 5 and minus 0.7. So
5 times 1, 2, 3. No. Doesn't.
yeah, so if you take 5 times of the first vector and take minus 0.7 times of the second vector, it almost gives you the third vector. I mean, it's not exactly the same, but it's very close to that value. So I think let me tweak that a bit. Let me see what value it will give me.
Obviously, the first one is 5 by 7, right? I mean, which is close to 0.7. But if I do that 5 by 7 to 2, so 10 by 10 minus
2.8. Yeah, that's right.
10 minus 40 by
15 minus 9 is 4. Yeah.
10
No,
minus
15 minus 9 is 6. Yeah, it's not exactly
40 by
coming.
30 by 7 is close to 2, and then 15 minus 6.3. It's 9, yeah. So it looks like slightly more than 0.7. So
10 minus. Maybe something else. 14 minus 8 is 6. 21 minus. No.
Okay, let's not focus on the mathematical part. Let's not focus on. I mean, we know that it lies on the span, so there is some coefficients that lead to this vector. I mean, we got pretty close by taking 5 and minus 0.7. So we observed that, and we can also take any other example for linearly dependent set in R3. You need not take plane and I mean you need not take 3 vectors where 2 are linearly independent. You can also take all 3 vectors to be linearly dependent on each other, right? That also forms a linearly dependent set. Obviously, if you have 3 vectors lying on a plane, that obviously forms a linearly dependent set as well. So yeah, carry on.
This is kind of easy to see. Like, it is covered like Kalman and that's You just add them, you get the third vector. So yeah. 26th question is if U, V, W are such vectors in the set that can be in any of the same set, it's called. Yeah, okay. Yep, it's called a linearly independent set. So when we discussed linear dependence, it means that no vector in the set can be like we saw the exact opposite, right? So if it's not linearly dependent, we can come to the conclusion that it's linearly independent. So in this case, like Chetan, if you want to do it using GeoGebra or
Yeah. So if UV are such that no vectors in this
no,
set. Okay,
oh sorry, we'll share again.
so it was that if UV W are such that no vectors in this set can be manufactured by any combination of vectors in the same set, then such a set is called a linearly independent set, right? So we know that, okay, as long as for two vectors, it's always very easy, right? For two vectors, it's not even a problem. You only need to see if they are some multiples of each other, right? If they are not some multiples of each other, you need not even worry about linear dependency in that, right? It's very easy to figure that part out in two vectors. But what is how do we figure out the whether, okay, just give me a second. Let me hide all of this. Yeah, perfect. So we have these two vectors, right? They're not they're not multiples of each other, right? We can see that clearly here. We can see that they're not multiples of each other. So since they're not multiples of each other, they are linearly independent. That means even if I take either of these two vectors, scale them up and down, I can never reach the other vector. It's not possible. Not possible for me to reach the other vector. Let's take an example, some random example. I want some really random example this time. Can anyone give me some random example for a vector? I mean, more random than the previous example that we took, 0 to 4. We want to increase the entropy for that randomness. Anyone?
Five, six, like and 0.
5, 6, and 0. Okay.
0.
5, 6, and 0. So this is my vector, right? This is my vector. Let me see. Okay, perfect. Can you? Okay, I have changed the color for this so that it's clearly visible. So it's a vector. It's a vector, red vector, right? You can see here. Let me take the linear combination of the first two and see if I can reach this vector. This red vector. Can I reach this red vector by taking some linear combination of the first two vectors? Can you look at the span of those two vectors? Everyone? What am I getting here?
Yeah, we are getting a plane.
We're getting a plane, right? We are getting the plane that we formed earlier. So let me just quickly plot that plane. Now, do you observe that although these two vectors are lying on the plane, obviously since they are linearly independent vectors, they are going to form a plane instead of a line, right? Additionally, we observe
Yeah, go ahead.
So additionally, we observe that no matter what value I change for this A and B, no matter what value I change for this A and B, let me just open that. Yeah. No matter what I do, if that resultant vector will always lie in this plane only. It can never reach this red vector. It can never come out of this plane. This is that example that Nishan took that day. That worm is on walking on a ground and it can never reach a wall, right? So no matter what linear combination of these two vectors I take, I can never reach this red vector. I can never manufacture this red vector. These three vectors, 5, 6, 0, 7, 8, 9, and 1, 2, 3, form a linearly independent set. And the vectors 1, 2, 3, 7, 8, 9, and 0, 2, 4 form a linearly dependent set. Since we could manufacture 0, 2, 4 by taking some linear combination of 1, 2, 3, and 7, 8, 9. Maria?
Yeah, just a minute. And I think most of these questions require more like you don't have much to write actually.
Can you look at the question number 27? So give examples of linearly dependent set in R3 and R2. Get conversant with the definition. Okay. So for this I mean if we want to verify it, if they are linearly dependent and independent, we'll obviously need GeoGebra. But can anyone give me some examples for linearly dependent set in R3 and R2? Some random examples.
I can tell you the geometrical interpretation of it.
Yeah, go ahead, Nishan.
So what we basically mean by linearly dependent set geometrically is that if we are going to take third vector, as I previously said, it is very much understood that two vectors are going to span a plane, given the fact they are not lying on each other.
Right.
They are not one and the same vector.
Correct.
If there are two vectors, they are going to span a plane. We also explain what we mean by spanning and all the technical jargons related terms. So it is very obvious that two vectors are going to constitute a plane. We have understood up to this point. The question is, what about the third vector? What about the fourth vector? What about the fifth vector? Where it's going to lie? Is it going to lie on the plane or away from the plane? So as Chetan has explained up till now, that any vector which is going to lie in the span of two vectors is linearly dependent vector. Am I right, Chetan?
Yeah.
Geometrically, of course. Fine. Similarly, the question is, we have to give an example of linearly dependent set in R3 and R2. So when we talk about R3, and when we talk about dependence, what is the, of course, if we are going to go analytically, we can do some calculations and come up and say that, okay, this set is linearly dependent and this set is not really, and this set is linearly independent. But what is the geometrical interpretation of the same in R3? So I guess yesterday or a couple of days back, we were discussing about hyperplanes. We know that R3 constitutes of many hyperplanes in R3 passing through the origin. So given two vectors, we will have a plane passing through the origin. We will have a third vector passing through the origin. We will have a third vector passing through the origin. We will have a fourth vector passing through the origin. We will have a fifth vector passing through the origin. We will have a sixth vector passing through the origin. We will have a seventh vector passing through the origin. We will have a If it lies on that hyperplane, it will be linearly dependent. But if it lies on some other hyperplane in R3, which are infinite by the way, then it will be linearly independent. Fine. This is the geometrical kind of visualization. It is actually whatever we can see with our eyes is kind of very much gives us very much a deep imprint. And by deep imprint is we do not kind of forget it for a long period of time, whatever we see with our own eyes. Rather than just mark up things in our brain, some numbers and some definitions. That's why we made a kind of geometrical approach, first-hand geometrical approach. And of course, we can show it with the help of examples. What do we mean by being on a same hyperplane? That is to say, what do we mean by being on the same plane? What do we mean by the dependent vector on the same dependent vector? By dependent vector means we have two vectors. We have got third, fourth, fifth, any number of vectors. Are they lying on the same plane as the first two vectors or not? This is the whole story of dependency and independency. This we could apply this in R3 plane, R2 plane, R1, R3 plane, R2 plane, or any Rn plane. If two vectors will always constitute a plane, and if it is R2 plane, it is a plane, x and y direction plane. But if it is an R3 space, then we will have infinite number of such planes, and we call those planes hyperplanes. If those planes are lying in R3 dimension, then we call them hyperplanes in R3 dimension. If those planes are lying in R4 dimension, we call hyperplanes those planes hyperplanes in hyperplanes in that Rnth dimension. And in each dimension, or or to say in a given dimension of a space, in a given n-dimensional space, we have got a plane, and we have got to predict or kind of we have to kind of make sure that given a vector, whether they lie on that plane or not. That is all what we mean by dependence and independence. And it is very obvious that dependence or independence is kind of a relative term. These are not absolute terms. It has to be dependent in regards with something. Something cannot be independent on its own. There has to be some reference point, and as I explained, the reference point are the two vectors which are going to constitute a plane. And of course, those planes could be hyperplanes in any dimension.
Okay. Let me just elaborate on that term once again. So, see, the very definition of a hyperplane is that, say, you are in nth dimension. Any object of Rn minus 1 dimension is a hyperplane. Okay, so say a plane in R2 is a hyperplane for R3. That's it. Coming to, I wanted to just discuss this because Bharat had posed a question in chat that is hyperplane linearly dependent in both R3 and R2? So what is the hyper? So this idea I wanted to clarify because the hyperplane in R3 would be all planes passing through the origin. And if you take any vector on a plane, okay, any vector on that plane, it is linearly dependent on other vectors that lie on that plane. What would be the hyperplane for in case of R2? What would be the align, right? So any vector that lies on that line would be a linear combination of other vectors that lie on that line. Bharat, does that answer your question? Uh, okay. Yes, they are independent. I didn't get you, Bharat. I just said that any vector that lies on a hyperplane is linearly dependent on other vectors that lie on that hyperplane. Or did I misunderstood your question?
See, Bharat, it is very important to kind of differentiate between a hyperplane and a n-dimensional space. Let us not confuse the space with planes, hyperplanes. Fine. As I just explained, we have R2 plane and we have R2 space. There is only one plane in R2 space. However, there are infinite number of hyperplanes in R3 space passing through origin. So this is what we are kind of guessing. We are being given third vector, fourth vector, and n number of vectors. We have got a kind of guess whether they are on the same plane or whether they are on the same hyperplane or not. If not absolutely, then approximately at least this is the gist of linear algebra. If we can kind of relate them, and by relate we mean kind of we can establish some kind of relation between them. If they are on this, they are on the same hyperplane. All the operations that we do in linear algebra is dependent on this fact, I guess. Isn't it, Chetan?
Yeah. I was just looking at the chart. I was just trying to ask Bharat if I have misunderstood his question. So, I don't know what Bharat meant there, but any vector that lie on a hyperplane is
The
linear
question
combination.
is the question is asking is that is hyperplane linearly dependent in both R3 and R2?
See, that's what I'm
See,
saying.
one second. Why are you talking about a hyperplane being dependent on some other
Exactly.
hyperplane?
Exactly.
So
That's
it
what
is
I was
vectors
coming
which are
at.
dependent,
Correct.
which are dependent, and the plane we are talking about is the geometrical interpretation of it. Let us not mix these two things.
So
The-
when we talk about a plane or any hyperplane that exam for that matter, we are not treating them as one entity. It's just for our convenience that we like to think of that them as plane. Essentially, what uh, they are a set of vectors. Okay, they are a set of vectors. So any plane we think of, any hyperplane including, we think of is just a set of vectors. So we can talk about linear dependence in terms of vectors, but it does not make sense for me to even think about linear dependence of planes. How are we going to uh, even figure that part out? Okay. Yeah. Go ahead, Madam.
Yeah, so another way, like we can think about it is like we obviously saw like this is a general case, right? If you have to construct a dependent set, there is a case when you have uh when the span is a plane, like you have the three vectors all lie on a plane. That's one case. What's the other since we took it in, like we discussed in this geometric manner, what's another way you can find three dependent vectors in R3?
That is to say, mathematical way of
No, not
looking at that.
mathematically, like geometrically itself. Like,
Okay. So kind of relating it with day-to-day interpretation, how it goes is like we oftenly say that if we want to come to a conclusion, we have to be on the same page. And
Correct.
in
Yeah,
many
I'm
times,
just
and
saying, like this is like we have to consider all linearly dependent sets in R3, right? See, so we saw a case where all the three vectors or maybe n vectors, like you can have a linearly dependent set of any size, will lie in a plane. Like they're all lying on a plane of dimension 2. Now, what's the other possibility that we have in R3? Like all the vectors, yeah, I almost said the answer. Like, yeah, what can they actually form?
Anyone? Guys?
We have very few participants, so I think I'll just.
Right.
Uh, yeah, so since we actually discussed it in this context, instead of taking numerical examples, so like when we discuss in this context, like you guys get the idea better. Like one numerical example might just give you a general idea, but yeah. So this now lies on a plane, right? So what's the next possible case? Like, yeah. So the answer was that, yes, since it's being comparatively quiet, is that once we consider that all the vectors lie on a plane, the next possible case is that all the vectors lie on a line, right? That would also form a linearly dependent set.
That was the first thing that we discussed when I had to interrupt Nishan. He was discussing the plane. I had to interrupt because I wanted to clarify this point that vectors that lie on a line also form linearly dependent sets. But you can manufacture any vector on that line using a linear combination of any of those. You don't even need to take you just need to scale any of those vectors to get that. So that's the linearly dependent set, other linearly dependent set in R3.
Yeah, so
All
something
possible
like,
lines.
yeah. Uh, all n, like we're taking all when n vectors lie on a line. Like I hope like even R3 you can have a line, right? So all the vectors
Mhm.
lying on a line means that the span of these vectors is actually a line. So that's of dimension 1. Yeah. Think yeah, so
Yeah.
any other examples in R3 we can actually think of? Or is this the end of it? Maybe I'll write one numerical example just for the sake of it. Something like 1, 2, 3.
I guess we have shown this on GeoGebra, right, Chetan?
Yeah, we saw
Yeah.
this on GeoGebra.
Then I guess we can take one more numerical example and move on. And
Okay, okay.
maybe we can also
You're
try
talking
showing
about
that.
the questions. Okay, okay.
Uh,
So yeah. Can we take a look at the next question, Maria? We've discussed this, right? We've discussed all the.
No,
okay,
we
Okay,
Chetan,
will
let's
take.
just do. Okay, yeah.
one
Let's do the
second.
R2 as well. Yeah.
One second, Chetan. Have you shown that? Have you shown this that okay? There are many. Of course, this is very much understood that there are many hyperplanes in R2 plane, R2 space. Fine. So have you kind of tried showing that that on a given plane we are given third vector.
Is it
There are two
just me or
vectors
Nishan's voice is breaking in between?
Yeah, your voice is breaking in between.
and now
Still
it's
breaking.
fine, I guess.
Yeah, it's cracking in between.
Yeah. I was
What
wondering. I thought it was my bad connection.
what about now?
Oh, perfect, perfect
Yeah,
now.
better. Yeah.
Okay, I guess. Okay, I'll try. Reconnect it. Now
Yeah, perfect, perfect.
Perfect, fine.
Yeah.
So I was saying that
Thank
okay, we know that there are n number of hyperplanes in R3 space, fine, and each space, sorry, in each hyperplane. Am I audible?
Yeah, you're audible. I think I said perfect too soon.
So I was saying
It's
that
again
we have
breaking.
many. It's again the
Yeah,
sound is
yeah.
like breaking again.
Yeah, it's cracking in between. That's why I said that I think I said perfect too soon.
Oh, now it would be fine, I guess.
Yeah, it's perfect now.
So I was saying that is there any change in kind of voice?
Oh, it's very much clear now. It's very much clear now. I prefer it this way.
Okay. So I was saying that we have n number of hyperplanes in R3 dimension.
Yeah.
So have we shown this in GeoGebra that by taking that various planes, multiple planes, not just one plane,
Okay,
maybe
let me.
take 2 or 3 planes
Mhm.
and take corresponding dependent vectors in those planes and show that okay, by
Mhm.
dependent vector we mean vector that lie on the same plane.
Mhm. Right.
Fine,
See,
fine.
I was not
Not
heavily
just one.
relying on.
So
Mhm.
if we kind of give just one example, now they think
Mhm.
that okay, this is just
Correct.
they do not
Let
get
me
the
do it.
other hidden part of it.
Let me not ask everyone else to for the points. I'll plot some points of my own choice.
Sure, absolutely. So that we get different planes as well. No?
Yeah. Okay, it's lying on the same plane, is it? Oh, no, it's not. Thankfully. So,
Just keep taking 2
We were
vectors and making
discussing
planes out of it.
linearly dependent sets, right? So should
Hmm.
lie.
Now take 2 vectors, make plane out of it. Again, take 2
yeah,
vectors, make plane out of it. Do it for the third time, and then try showing dependent vectors on all those 3 planes.
yeah. Just a second. Can
So if
you?
you realize, in the statistics too, we are often given in question very in more than 50% of the questions I saw that in a given probabilistic plane, this is what is often mentioned, in the question.
Can you look at this now? That I
There
took
are 2 planes.
those 2 vectors. I took these 2 black vectors. See, the GeoGebra is not responding properly today. In my case, I don't know why. So yeah, can you look at these 2 vectors? They are lying on this plane, right? These 2 vectors, and along with these, any other vector that lies on on this plane actually form a linearly dependent set. But if you take this blue vector along with these 2 vectors, these black 2 vectors, then they won't form a linearly dependent set because this blue vector does not lie on the span of these 2 black vectors. So then they form a linearly independent set. And since just like how we formed this particular plane, we can actually form n number of planes passing through the origin that lie in R3. Okay, if you want, I can plot another one. Let me just do it so that its idea is clear. Say I take -2 comma 5 comma 3, and so I took another vector that is okay. Yeah. So let me take this plane that forms these 2 vectors. Okay. Yeah. So -5, -3, 1. -2, 5, 3. Perfect. Can you look at this now? I have 3 planes now in R3 showing me that. Okay. Yeah. Right? 3 planes passing through the origin. 3 planes passing through the origin. And just like these, I can get n number of planes passing through the origin. And every vector that lies on one plane is just a linear combination of the other vectors on that plane, is linearly dependent on other vectors on that plane. And the set of vectors that lie on a particular plane form a linearly dependent set. Any subset of those vectors as well form a linearly dependent set. So I guess this was what is there anything else, Nishan, that you want me to elaborate here?
No, I guess this is all.
Yeah.
You can, I guess, move to next question.
Yeah.
We
Okay.
haven't discussed R2 actually. Yeah, maybe we'll discuss that. I mean,
I think
R2 plane. So when we talk about R2 space, there is only one plane possible. That is R2 plane. That is X. That consists of X and Y coordinates, isn't it? I'm saying it very much commonsensically, you know. So any vector we are going to take in R2 is going to give us a linear combination, isn't it, Chetan?
pardon?
Any vector that we are going to take in R2 is going to give us a linear combination.
Is going to give us
I did.
a linear combination. I didn't understand that.
Any vector that we are going to take in R2 is kind of going to lie in the span of first vectors. Given we have R2 space.
Yeah, if we take 3 vectors.
This is something unique about R2. That was not the case.
Not just unique about R2. You take R3 as well.
No.
In R3,
what I'm suggesting is that if we are going to take any random vector, for example, in R3, it may lie on some other hyperplane. But since there is only one plane in R2 that is passing through the origin,
that's what I'm getting
any
into.
vector,
So,
any vector if we are going to take, it is going to become a linearly dependent set.
Yeah, I'm coming to that. So in R2, you need 2 vectors to span the entire R2, 2 linearly independent vectors to span the entire R2. The moment you get those 2 vectors and you add a third vector to that set, that's always going to be linearly dependent on the first 2. Okay. This is not unique to R2. You take R3 as well. In R3, one vector will give you a line. 2 linearly independent vectors will give you a plane. 3 linearly independent vectors will give you the entire R3. The moment you add any fourth vector to that set, that is going to be linearly dependent on the first 3. The moment your number of linearly dependent vectors equals the space you have, okay, the dimension of the space you have, any vector that you add afterwards is going to be linearly dependent on this. You can not have a linearly independent vector afterwards.
Yeah,
That's
so
it.
if so if our vectors are in say Rn, if you have an n+1 vector, that would form a linearly dependent set.
In case, assuming that you have n linearly independent vectors
Yeah,
already,
n linear. Yeah.
already, assuming that.
Yep.
And in other words, I mean, okay, let's not go there. Okay. Yeah.
Maybe it's discussed in the questions, I guess. Like
Yeah,
it will,
it will come, I think. It will come in the
yeah, and then we
upcoming
can
video.
discuss it.
Yeah,
Yeah.
yeah.
So in
I,
this case, in R2, when we have like a linearly dependent set of n vectors, they all should lie on a line. I maybe I could have written an example too, I guess. One example could be something like 1, 2, 2, 4. So basically, it lies on a same line because you can see that 2 times 1, 2 is 2, 4. So it lies on a line. So all the vectors need to lie on a line. If we are in R2 and we need a linearly dependent set. But if I'm in like the question just asked for R3 and R2. So if I'm in R4, I can have three possible cases. Like all the like if I have n vectors, all the n vectors consist of only three independent vectors. So they essentially span a plane, a hyperplane of 3 dimensions. Then what's the possibility is that in that set of n vectors, you only have two independent vectors. So they span a plane of dimension 2, or you have all the vectors lying, you have only one independent vector and they all lie on a line. So we can actually generalize this when we have higher dimensions too. We have got the idea of how it works. Yeah. So I guess that's enough for this question, right? We
yeah,
can
so
move to the next one.
are 1, 2 and 3, 4 linearly independent in R2? It's very simple. The moment you have two vectors in any dimension, okay, in any dimension you have two vectors, it suffices to check if they are just scalar multiples of each other or not. Okay,
Or maybe
that's it.
since we are going in the geometrical route, we can say that if I take a line that is from the origin to the point 1, 2, and if you draw a line, this point 3, 4 is not on the line formed by 0, 0 and 1, 2. So it's not linearly dependent. And you can say it's linearly independent. Since we were going in the geometric way, yeah. Or easiest way to check is that like it's pretty obvious, right? 3, 4, like if you multiply 1, 2 times 2, you'll get 2, 4, which is not 3, 4. You won't get anything like this. So proving, I guess we can write that like 3, 4 is not on the line. Formed by origin and 1, 2. Any other explanations or anything you guys have a doubt in this? Uh,
So, I mean,
or you
we
can check,
just
like, I'll write the scalar multiplication part also, I guess,
yeah. So
because
you take any scalar multiple of any of these vectors, any one of these vectors, you can never reach the other one, and that suffices. That's it. That's the only thing you need to know. Swapnil said earlier that if your vector lies on the span, okay, then that's linearly dependent. If it does not, then it's linearly independent. So the moment you take any scalar multiple of a vector, you're going to get a line. If the second vector lies on that line, it's linearly dependent. Otherwise, it's linearly independent.
talking about line before. But like, yeah, if you want, you can type in the chat, like what you meant by contradiction. Try to show that they can't be dependent.
It
Are you
28th
talking
one,
about the
suppose
method
you
where you
can
take
use.
alpha times and you try to solve the equation? I mean, that's the only thing, like, but that would be too mathematical. So this
Try to
is an
show they can't be dependent.
by contradiction. Maybe you can elaborate on that.
Yeah. I mean, we by contradiction. So, are you saying that that we assume that they are dependent and try to see if with some scalar quantity we with what scalar quantity we can get that vector? Is that what you are suggesting, Bharat? That with what scalar quantity I can get the second vector? Is that what you mean by contradiction? That I'm assuming that they are linearly dependent. So there must be some scalar quantity that multiplies to the first vector that gives me the second vector. But since there does not lie any such scalar quantity, I'll have to contradict my earlier assumption that they are linearly dependent. That means they are linearly independent in that case. Is that what you're suggesting? Okay, understood. Okay, yeah, if you want that, I can show that on GeoGebra. I think that would be much easier to visualize. I'm not using the GeoGebra today a lot because every time I'm using it, my system is hanging. So I don't know what's happening today. Maria, can you share your screen maybe if your system is not my system is not supporting me today. I don't know why.
Sure.
So just open G. Understood, Bharat. Understood. So we assume that I have two vectors, that 1, 2, and 3, 4. I'm assuming these are linearly dependent vectors. That means I can get 3, comma 4 by taking some do vector of A. Yeah, perfect. Now do vector of 3, comma 4. It was 3, comma 4, right? The point. Do
Yeah.
double bracket, sorry. 3, comma 4. Perfect. So just remove the A. We don't need the A. So we already have our two vectors. Remove the A.
Yeah, but I've
Hi-
defined
Hide,
you
I meant.
using.
Hide.
Okay.
Okay. So you change the color for this, maybe, yeah, choose the red. For the other one, you take another color, maybe take the blue one or something. Uh, for
Yep.
the other.
This is the.
Yeah, it's fine. It's fine. So let's we are saying that both of these vectors are linearly dependent on each other. Let If we are assuming that, then some scalar multiple of one of these vectors can lead me to the other vector, right? So can you multiply? Can you just choose one and multiply it with some scalar quantity, Maria? And can you
Yeah.
trace that? Can you trace that as well? So do A times, say U, or A times V.
1 second.
Yeah.
That's my mouse. Okay.
Yeah. So what are we observing here? We multiplied some scalar quantity with our u, okay, and we observe that we were getting a line, but our red vector was not lying on that line, right? Now we are trying, okay, maybe it wasn't working because we took that vector. Let's take the other one. Maybe let's try to multiply some scalar quantity with that vector. Let's see what happens then. Are you?
Yeah, let me just shift this now.
Yeah.
Isn't it? Oh, is the color not bright enough? B times V, right?
Yeah, B
Oh, okay,
times.
okay. It became an equation. Okay, okay. Oh, because I used the variable X, I guess.
Yeah.
Okay. It's not showing me the trace. Okay, I'll change that. Yep. So both of them are forming two different lines. They're only intersect at the origin. So it's clear geometrically that also that that's thought.
Right. So this contradicts our initial assumption that they are linearly dependent. Correct. Okay. Can we move on to the next question, Mary?
Yeah.
That was a very nice idea, Bharat. Thank you for that. We'll try to take the assumption that they are linearly dependent.
Yep. So R1123. Yep. R11237 17 linearly independent or linearly dependent.
Okay, let's do the same thing. Let's do the same thing. So
Okay.
let's assume one of these. Either they are linearly independent or linearly dependent.
It was 28, right?
Mhm. So just
Let me just see. I have to open a new tab. I don't.
Maya, can you copy and paste that link once again?
Why? What's the issue? Oh, okay. Send it to you alone. Okay, okay.
Perfect. So
Oh, the
let's.
trace is gone. Yeah, that's very nice.
Are we
Yeah.
using points in 3 dimension or 2 dimensions for this question?
We are in 2D and we are plotting 3 points.
Right. Okay. Let's assume that they are linearly dependent. Or we did dependent last time. Okay, let's do independent. That means that so if I take any two of these vectors and I take the span of those two vectors, the third vector should not lie on that span, right?
Should or should not?
Should not. I'm saying that they are linearly independent. I'm assuming that. I'm assuming that. So if I'm assuming that, then that condition must be fulfilled, right? That the third vector should not lie on the span of the first two. If it lies, then my condition fails. Then it means then they are linearly dependent.
Now, what we can do is that, we can just check if the W is in the span of the U and V, right? That's one way to check it.
Yeah.
So
What's another
let
way?
me
How we kind of check this geometrically, or to say intuitively? Is my voice clear now, Chetan?
Yeah.
Or it's
Perfect.
breaking?
I mean, it's clear as of right now. It's clear.
Okay.
I don't know. I don't want to jinx it. Okay, I don't want to jinx it.
I guess
Yeah.
this cord has kind of malfunctioned. I'll have to order a new one.
Yeah.
Because when I'm removing
We
it,
need a Kalman filter to clear the voice.
okay.
We actually need to discuss that concept. We need your help with that.
no, in previous 2 or 3 discussions only, I realized that okay, it is all about linear dependence only in this complete linear algebra thing. Whether it was question of pixel thing or today what
Right.
we were talking about Kalman filter, it was all about how things are kind of correlated, and that's why we also talk about correlation. So we kind of predict or find the missing point of correlated things. First of all, we kind of plot them on a matrix and carry out mathematical operations. And those mathematical operations are only possible because they are kind of dependent.
That's how you were able to come up with the missing value, right? That's how you were able to come up with that because we assume that that column is going to be some linear combination of the other columns.
Yeah.
So
This question, it's better to think about it intuitively than graphically, right? Because
you can get
okay,
What I mean by graphically is kind of what I meant by graphically. It was that okay, commonsensically I meant by graphically.
yeah.
There is no third place. There is no other place to go. The third vector is but bound to lie on the plane, on the plane of first two.
Yeah.
So what
Yeah, what
was the
Nishant said is is something we kind of said that in between, and we thought we were like kind of like we wanted to see if there was some question related to that, and then immediately it came up. So it's actually nice. So yeah, when we take any two vectors, what can we reach or what can we manufacture when we get two independent vectors? We get a plane. So when we are in R2, you can manufacture any vector in R2 using just two independent vectors, right? So it actually spans the entire R2. So if you take another third vector in R2, it's bound to be dependent on the first two vectors, right? Because you can get the third vector can be manufactured by using the first two vectors because you're in R2. You can't manufacture something beyond beyond a two-dimensional plane using two vectors in R2, right? Hope that was clear. Three vectors in R2 are always linearly dependent if they don't lie on a line. Yep, that is, if you have a set of n vectors, or if you have a set of, say, 4 vectors in R2, and if you have two independent vectors in that set, then the entire set is going to be dependent. Or unless all the that someone mentioned in the chat is really nice. Unless all the vectors they 1 second R2 are always linearly dependent if they don't lie on a line. If they lie on a line, also they're dependent, right?
Yeah.
Line also is lying on the plane itself now.
See,
It's just like that we are not beta
okay.
is 0.
Okay, let me take this one. I think 2D graph, I think the system can handle. It's only the 3D graph it needs the computational power. Let me just try and change it to the 2D. Okay, it has
I
already.
mean, it's the same thing, right? Is there anything else you want me to plot? Like I've already done.
No. That was
most
it.
of it.
I mean, okay, it has. Okay, perfect. I guess it doesn't want me to do it. Share my screen. Okay, Maria, can you forcefully share the
Should I
screen?
stop sharing?
No. You share your screen. Forcefully share the screen.
I
I
can
can't.
share. Like I am sharing my screen.
Okay. It's showing that.
I'll stop sharing.
No. My system is hung now. So you continue with the
Okay.
questions. I can't.
Yeah. So the thing is that the idea here is that when you have two independent, like first thing we need to observe is that how many independent vectors do we have here? Since we already talked about, I think we did, right? So how many independent vectors are there in 1, 1, 2, 3, and 7, 17? They're all independent, right? None of them are multiples of each other. You can't manufacture. Can you see any pairs that are? Yep. Okay, maybe I was going in the wrong route. Yeah. So the point is that you take forget about 7, 17. You just take 1, 1, and 2, 3. Forget that R exists. You can create any point in R2, any vector in R2 using just these 2 points, just the 2 vectors. Because then both of these two don't lie on a line. So what Himanshu meant is 3 vectors in R2 are always linearly dependent if they don't lie on a line. Do you mean by they? Do you mean all 3 of them lie on a line, or any 2 of them lie on a line? I guess that's the part that is a bit confusing. So these 2 vectors, you realize that they do not lie on a line. So what can you manufacture with these 2 vectors? You can manufacture the entire R2 using these 2 vectors. Now, the third vector that I'm taking is just another vector in R2. So the question, isn't it kind of obvious that this third vector or third point can be manufactured by these 2 vectors? So that's the only idea you kind of intuitively need. Like if you have n vectors, you have n independent vectors, you can basically create the whole n-dimensional plane. And then you take the another n plus like some other vector that is not in the span, like some other vector, and you're only having n dimensions, then that last vector is bound to lie in this n-dimensional plane. Because you don't have anywhere else that vector can actually go to. So that's the idea here. So when I have like 3 vectors in R2, there are always going to be 3, let me say 3 vectors in R2.
Okay, so we have two vectors. We take any two vectors. They are not linear. They are not scalar multiples of each other, right? One. Anything you multiply to one, you can never get 2, 3, right? So we know that they are linearly independent. And once we have two linearly independent vectors in R2, we know we can span the entire R2. We can get any point in R2 with just those two vectors, right? So if we have that, then we know that any vector that I add to that set, that's going to be linearly dependent on the existing two. It's impossible to have 3 linearly independent vectors in R2. Impossible.
Yeah, what Himanshu said is if they don't lie on a line, if the 3 vectors actually lie on this on one line, that's also a possibility, right? Then also there, like I'll take an example like that. If I have 3 vectors 1, 1, 2, 2, 3, 3, this is pretty straightforward, right? This first 2 times the first vector gives you the second vector, 3 times the first vector. This is also linearly dependent. So
I guess
isn't it
question
the general
also,
conclusion that if we have 3 vectors in R2,
as long as they are at least 2 of them are linearly independent, they are always going to be linearly dependent.
no, but we just took one example, like in here we only have one independent vector, right? In that case also it's linearly dependent.
I was just trying to get that idea that okay, if you this is true that if you, even if you have say 2 vectors that are already linearly dependent, you add that to the set, it's always going to be linearly dependent, right? So if you already have 2 linearly independent vectors and you add another to it, it will be linearly dependent,
Yeah.
right? There we had linearly independent set, so anything that we add, it will be linearly dependent. Here we know that they are already linearly dependent. 2 of them are linearly dependent already, so the third one if I add, it doesn't matter if it's linearly independent individually with those vectors. The set as a whole will be linearly dependent.
So that was the idea in question number 29. Maybe we can go to 30.
Yeah. I think, can you just take a look at the question number 30? Okay, maybe we can take it. Maybe we can take this question tomorrow. Maybe
Yeah, it's
these.
already close to 12. Yeah.
Right. 30 and 31 seems pretty linked to each
Long.
other. So yeah, not long. I mean, they link seem linked to each other. So let's just take
I
this
guess we have
tomorrow.
kind of already discussed the just. This is just we are going to pass it through very
Correct.
quickly.
Yeah.
So, anyways, we'll take it tomorrow.
Yeah. That we
9 to 12 are the core hours, right?
right. Sir.
Good.
Yeah, we
So
usually conclude by 11:30. I think, yeah, today.
I mean,
I
not
didn't notice it.
So
it's
the idea is to maintain the momentum over a long period of time. So if the sessions become 4 hours, 5 hours, becomes difficult every day to join because you got assignments, other
Right.
work and all that. If you keep 2-3 hours, then everybody comes. Then you can plan your schedule around it. Today I had to have dinner. I had to turn my video off, finish the dinner, and come back. But yeah,
I still haven't, sir.
yeah. So now maybe I'll